Thank you, Simon, and good evening, everybody. I'm really excited to share my talk about the work I've done so far in my PhD. So more about epitaxial growth of halide perovskites. So the title here says layered metal halide perovskite by pulse laser deposition. So I will be introducing this technique to you today. So Simone also briefly said a short introduction for me, so thank you. So I'm a PhD student, and our group is situated in the Netherlands, in Enschede, a tiny, beautiful little countryside, and the campus is really beautiful. So the image right here you can see is an overview or an aerial view of our campus, and the star is where our labs and offices are. So these are some images from our different group activities. Like many of you here, many of my group members work with halide perovskites. So, and then you know how the halide perovskites have the ABX3 perovskite structure and all their cool, amazing properties that make them very interesting investigations for solar cells, lasers, and many more applications. But all these applications are being explored in their nanocrystal form or in the polycrystalline thin films or as bulk single crystals. But what about epitaxial halide perovskites? So we know that these halide perovskite materials have different polymorphs or can be in their cubic, tetragonal, or orthorhombic phase. But if we grow them epitaxially, can we control the polymorph formation, thereby gain structural stability, and also gain control over the film orientation? And in doing so, can we move towards single crystal thin films, which probably have a lower defect density and provide an improved optoelectronic properties? So that is the question that I will be trying to answer during my presentation today. And for the deposition techniques itself for metal halide perovskites, as this image right here shows, there are several deposition techniques available to synthesize metal halide perovskites. So if we broadly classify them, they can be classified as solution processes and vapor phase deposition techniques. So when it comes to solution-based processing, it's much more explored compared to the vapor phase deposition technique. But what about PLD for metal halide perovskite growth? So solution-based processing do offer a simple fabrication and also have films which are much more defect tolerant. But when you have vapor phase growth, it's a dry processing technique, and you're also able to control the thickness. And if you want to move to development of heterostructures, it is very convenient. So here I'm going to be introducing to you the vapor phase deposition technique called pulse laser deposition. So as the name suggests, there is a pulse laser source which ablates your target. So it shoots on your target, and the process called ablation takes place. So what happens in the ablation process is, as the laser shoots on your target, there's a local melting of the very topmost layer of your target, and then the formation of a shock wave, and that's how the plume is produced. And this plume undergoes gas phase reaction because of the background gas in the vacuum chamber. We introduce an argon gas. And in the direction of the plume is where we place the substrate, and that's how you have your film growth. And for the PLD itself, there are different parameters that you can tune to grow your film. Starting out with the laser. So there are different lasers available, and depending upon the laser, all the properties of how the ablation is also changing. But we have a UV excimer krypton fluoride laser. So for the laser energy matters. So that is how you ablate the material from your target. And then the spot size. So the spot size, as the schematic shows here, if you have a small spot size or a larger spot size, depending upon the size, the amount of material you remove from the target to create the plume is different. So that controls your deposition rate. So together, the laser energy and the spot size is how we define the term called the laser fluence, which is the laser energy per spot size that you use on your target. So this is a main parameter for controlling the deposition rate. Another important parameter in pulse laser deposition is the laser frequency. So this is how fast your laser shoots on your target. Though it arrives at pulses, you can go to very high frequencies of 40 Hertz or very low frequency of 1 Hertz. And next is how do you control the plume itself. So the deposition, so the entire system, like the target, the film, the sample is all in the vacuum chamber, but it is not under vacuum. So we use background gas of argon to control the gas phase interaction, or how the plume itself is forming in the chamber. And since the argon, depending upon the pressure you use, if you use a low pressure or a high pressure, you have much more collisions of the atoms, the species in your plume, and reducing the kinetic energy. So the background pressure, you're able to control the kinetic energy of the species arriving at your substrate. So choosing a background pressure that is suitable for your sample or your material is very important. And here we have a case example of the double halide perovskite, where we see for a pressure of 10 minus 2 millibar, the plume is much more widely spread, and for a higher pressure, then it's much more confined. And for a higher pressure, usually there's much more collisions before the species actually arrive on the substrate. So you're able to lower the energy of the species arriving on your substrate. And then finally, the target material. So this, depending upon which halide perovskite you want to grow, you take the precursors, you put them, you mill them together and press them as a pellet. So mostly the targets for pulse laser deposition is more like a tiny compressed pellet with the material that you want to grow. So having introduced this technique, there's already been several studies of metal halide perovskites grown by pulse laser deposition, but all of this has been done in their polycrystalline form. And maybe many of you in the audience are interested about halide perovskite solar cells that have been grown by PLD. Then if so, I would refer you to these two papers which have been published from our group members. So please do check them out if you're interested. But in this work, the case example that I have been working on is methylammonium lead iodide. So a methylammonium lead iodide is a hybrid inorganic organic halide perovskite with the methylammonium inside the octahedral cage. The octahedral cage is built by the lead and the iodine. And we know that methylammonium is able to exist in a high temperature cubic phase, a tetragonal phase at the room temperature, and a low temperature orthorhombic phase. So the question we asked during the start of this research was, can we use pulse laser deposition and epitaxy to stabilize the high temperature cubic phase of MAPI at room temperature? So since we wanted to reach epitaxy for metal halide perovskites, there were several parameters that we had to consider. First being a good lattice match between the substrate and the film. So since your substrate acts as the registry for your film to grow, it is important to have a good lattice match. So for that, there's this nice schematic here which shows different substrates which are available for a different, so the pseudocubic lattice parameters of different halide perovskites, showing that the rock salts are having a good close lattice match with different halide perovskites. And in this case, we're working with methylammonium lead iodide, which has a close lattice mismatch with potassium chloride. So the lattice mismatch here is minus 0.6%. So we chose potassium chloride as the substrate. And the next step is to have an atomically sharp surface for the substrate, because this is the surface that the species arriving see, and this acts as the growth front for the film to grow. So for that, how we prepare the substrate is we cleave the potassium chloride substrate. So I have a potassium chloride substrate with the 100 out of plane orientation, and along the thickness, so along the 010 direction, we cleave it, exposing the atomically flat surface. So the AFM image shows the atomically flat surface and the terraces of the potassium chloride substrate. Along the line, you have the line scan, so the scan showing how the terraces look like. And next, the deposition method itself. So I introduced pulse laser deposition. So the substrate here is at room temperature, and you have a pulsed UV laser shooting at the target. So the target has methylammonium and lead iodide, but methylammonium in an excess. So an 8:1 ratio. So these powders are milled together and pressed as the target. So the laser shoots and the plume is produced. So for epitaxial growth, an important parameter to consider is you want to have a very low deposition rate. And for that, I used a frequency of 1 Hertz. So I give sufficient time for the plume to form and reach the substrate and have enough mobility to arrange themselves before the next generation of the material. And I tune the spot size and the fluence to arrive at a deposition rate of 0.7 nanometer per second. So this is a schematic of showing how the 3D perovskite methylammonium lead iodide would look on potassium chloride. So having grown the sample, well, we have to answer the question of if we can use PLD and epitaxy to stabilize the cubic phase of mapping. So we need to understand how the structure looks like. So I take it to the XRD setup. And like any other XRD setup, you have the degrees of freedom where you can do the 2 theta omega scan and the omega scan. Our setup in the University of Twente allows us to go maybe a few additional degrees of freedom. One is the phi angle, so you can rotate your sample azimuthally with respect to your surface normal, and also the tilt of the sample. And we have a 2D detector, which helps to make maybe quick imaging. Okay, so I take my sample, and the first thing I do is a 2 theta omega scan. And the XRD pattern right here shows, so we grew 3 different thicknesses, a 17 nanometer, a 40 nanometer, and a 15 nanometer film. And they're color coded as a dark red to light pink. And this color code remains the same throughout all the slides in the presentation. And below the XRD patterns, you see the reference pattern of the cubic, the tetragonal, and the lead iodide. And the black pattern is from the potassium chloride substrate. So from this figure, you can see that the yellow highlights show a clear indication of the out-of-plane single-oriented films that are grown for the thicknesses of 70, 40, and 15 nanometer. Then to check how the crystallinity looks like, we did the rocking curve on the 001 peak of MAPI, and we see that with the decreasing thickness, the full width half maxima also decreases, indicating that an improved crystalline quality. So we now know that the films are highly oriented, but we have to confirm if they're epitaxially grown. So for that, we did reciprocal space mapping. So reciprocal space mapping at the 420 asymmetric plane. So reciprocal space mapping is usually done to confirm epitaxial growths because you're able to get information both from the in-plane and the out-of-plane. So a quick way of understanding reciprocal space mapping is you're trying to do a couple of rocking curve measurements at a specific plane but at different 2 theta angles, and you put them together. So you're able to view both the substrate and your film in the same reciprocal space region. And here, the y-axis, the QZ, gives us the out-of-plane reciprocal lattice coordinates, and the QX gives us the in-plane reciprocal lattice coordinates. So the first image on the slide towards the left is a reciprocal space map of the 420 and just the substrate. The bare substrate indicating a bright red spot, which shows how crystalline the potassium chloride substrate is. And then moving on, I did also reciprocal space maps on the 15 nanometer, the 40 nanometer, and the 17 nanometer. With the 15 nanometer, the signal was very low, but you still see it right below the substrate. There's a little bit of intensity. And with the increasing thickness, it becomes very clear. So you have the potassium chloride substrate that is indicated by the black arrow and the film right below the substrate. And there's no shift in the left or direction indicating that it's epitaxially grown. And also the spot, which is highly crystalline and undistorted right below the substrate, so show that it's not a relaxed film, but it's epitaxially strained. Okay, then, so we confirmed epitaxial growth, but we also wanted to know if it's cubic in nature. So for that, we still do a reciprocal space mapping at the same 420 plane, but at the different reflections of KCl. So what we do is we rotate the sample azimuthally, so the phi angle is 0, 90, 180, and 270. So that gives us the different reflections. And as I mentioned earlier, you have the QX is the in-plane and the QZ is the out-of-plane lattice parameters. So if you see, the white dotted line shows the position of the film, and for all the images or all the reciprocal space maps, it's at the same point. So there's no upshift or downshift, indicating that there's no change in the out-of-plane lattice parameters or in-plane lattice parameters, showing that it has a cubic symmetry for mapping. So we confirmed now with these reciprocal space mapping that it's epitaxially grown and the cubic symmetry. But additionally, we did some XRD pole figure measurements to get information about how the texture looks like for the sample, or how the coplanar planes of the film with respect to the substrate look like. So how these pole figure measurements are made, if you're familiar with phi scans, which help us visualize the symmetry of the film, it's similar to that, but we do a phi scan at every tilt angle of your sample. So your sample rotates in the phi, makes one measurement, moves to the next tilt angle in the chi, so you move it, and then you make another measurement. So I have a tiny video to show how this measurement is done. So you go to a particular plane you want to investigate, do a phi scan, and then move it in the tilt angle again, and you do another scan. So this is repeated all the way from 0 to 80 to get your pole figure measurements. So in the next slide here, so you see the pole figure measurement of a 70 nanometer thick MAPI film on KCl for the 0, 1, 2 plane. So you see the simulated pole figure and the measured pole figures. So it's really nice that they look very similar, but what is the reasoning behind it is that, for example, if you take the 0, 1, 2 plane and the 0, 2, 1 plane, if they were in the tetragonal phase, the despacing would be different and you wouldn't be able to visualize them in the same pole figure. But since you're able to visualize them, we again confirm that the MAPI is single-oriented and has the cubic phase structure. And these planes cannot be represented or pictured for the potassium chloride substrate. So this is purely from your sample itself, the thin film, sorry. And then we also did electron backscattering measurement. So this is a nice red rectangle showing the smooth microstructure in the single orientation. So when I showed this image the first time in our group meeting, everybody was like, oh, did you just copy paste the rectangle there? But no, this is an actual measurement showing how smooth the microstructure is with a single orientation. Then we were also curious about the optoelectronic properties of the MAPI film. So we did photoluminescence measurement for the all thicknesses of MAPI, so the 70, the 40, and the 15 nanometer. And we see that there's a red shift as the thickness increases. So this suggests there's an epitaxial strain. So as the thickness increases, the influence from your substrate decreases. So you have a little bit of shift, but still all the films are in their cubic phase and their epitaxial. And the band gaps here are 1.66 electron volts or towards 1.66 in the thinnest film, indicating or having a very close band gap value reported for the cubic MAPI. And then we also did photoluminescence measurements over time. So we stored the sample in the glove box and we just took them out for measurements. And in this graph here, you see the band gap versus the number of days. And over several days of measuring, we found that these samples are very stable due to their epitaxial strain, that they stay luminescent for quite a long time. So to summarize, can we use PLD and epitaxy to stabilize the cubic phase of MAPI? Yes, we can, and that we found through or answered these questions through specular XRD and reciprocal space mapping, and also did pole figures and EBSD measurements to show on a large scale how they are single-oriented, and through the photoluminescence measurement also confirm that we have the cubic phase of MAPI. So for more information in the paper, we show about the DFT calculation and even the charge carrier transport measurements. So if you're interested, you can check them out. Unfortunately, it's not open access, but if you want a copy, you can send me an email and I can share the PDF with you. So having grown the epitaxial films and having gained a little bit of control over the growth of halide perovskites in an orderly fashion, we said, okay, let's move on to explore 2D halide perovskites. So 2D Rudolson-Popper halide perovskites are in the same family of halide perovskites, but now they have a large spacer molecule, an organic molecule that goes in between these lead octahedras. So they no longer have the ABX3 stoichiometry, but they have maybe a Rudolson-Popper phase. So that's the schematic right here. So what we tried to do was having the epitaxial film. So now we have the potassium chloride substrate, the epitaxial MAPI grown on top. We tried to grow a 2D PEA2 lead iodide layered metal halide perovskites on top of these epitaxial films. So the question we wanted to answer by trying to grow these films is, again, if we can actually grow these 2D Ruggleson Popper films by PLD, and if they were conformally grown. So this work is pretty new, and we've just submitted the manuscript and it's under review. But as a sneak peek, maybe some results that I can share with you today. So for the films, we did XRD. So we again grew 3 different thicknesses of the 2D PEA2 lead iodide on top of a 15 nanometer epitaxial film on KCl. And in the XRD pattern, we see that we're clearly able to see the n is equal to 1 phase of the 2D layer, and also, yes, the underlying the perovskite layer. So the red dotted line indicates the n is equal to 1 phase. And then we did GIWAXS measurements for these samples of all thicknesses. So the leftmost GIWAXS pattern is for the 20 nanometer, the middle one is the 40 nanometer, and then the 70 nanometer. So you see for the thinnest one, the n is equal to 1 phase, you're all able to see the n is equal to 1 phase in all the thicknesses, but as the thickness increases, there's a little bit of spread, showing a little bit of disorder as the thickness rises. And the next one we wanted to check was if they were grown conformally, but before that we did photoluminescence measurement. So here we are able to see the MAPI layer, the underlying MAPI layer luminescing as well, and also only the n is equal to 1 2D layer. So on the right side, you see the optical view and the different regions that we did spatially resolved PL, and you see that we have a conformal layer that's growing on top with the n is equal to 1 phase. So with that, I come to the end of my presentation, and I would like to thank all the collaborators who supported us during this research. Without them, it wouldn't be possible, and for my wonderful team and PI. And thank you all for listening. I'm sure you have questions.